Giant gravitons from gauge theory.
All right, so start.
Yeah.
All right, thank you very much. It's a pleasure to be back here in Swansea after a long time and see many old friends in person. My title is Giant Gravitons from Gauge Theory. So in this audience, I'm sure everybody knows what is gauge theory. Giant gravitons was a subject of intense research about 20 years ago, and there are people in the audience who have contributed to this. But time has passed, and there are many young people in the audience, so I'll just remind you briefly what they are. Essentially, the context is string theory in anti-de Sitter space. And giant gravitons are d-branes in anti-de Sitter space. Okay, so imagine some AdS5 times S5 or some other compact manifold, and you think of a d-brane which wraps some compact cycle. Okay. So from far, it just essentially looks like a point and moving around, and its quantum numbers are the same, conserved quantum numbers are the same as that of a graviton, so that's why graviton. But unlike gravitons, which are essentially massless, their mass is set by some background curvature, the mass of d-branes is set by the tension, which is 1 over the string coupling. So in perturbation theory, they're very heavy, so that's partly where the name comes from. Okay. Now, the title refers to a context of the ADS-CFT correspondence. So I'll always be talking about some kind of conformal gauge theories. And the bulk ADS dual has all kinds of gravitational objects in its spectrum, like gravitons or giant gravitons, black holes. And the question is, what are these? How do you identify these objects in the boundary theory? Okay? Is there a signature? Okay? And in particular, where are the giant gravitons? Now, this might seem like some question of very minute detail for ADS-CFT aficionados, but in fact, as I hope to tell you, it's a much more general question applying to a large class of gauge theories of the type that we'll consider. Okay, so I'll try to spend the first half of the talk explaining what the question is in quite some detail, and the second half trying to answer it. Okay, so please do interrupt with questions or comments. That helps a lot. Okay, so let's begin with some kind of a warm-up problem. So we want to think of holography and ADS-CFT. So you turn to your best friend, n equal to 4 super Youngman's theory with a UN gauge group. And in this theory, let's suppose we have the task to write down all local physical operators. Okay? So let's say even when the gauge coupling is 0. Okay? So how do we go about this? Well, first we list the fields of the theory. So there's the gauge field. There you go. Oops, there's a small delay. So there's the gauge field. There are the 3 complex scalars and their complex conjugates, x, y, z, the fermions. And if you want to write local operators, you're also allowed derivatives, and that's it. So this set of letters is all that you can use to write local physical operators. But now remember that these letters are actually matrix valued fields. So if you want physical, which means gauge invariant, you have to make gauge invariant combinations. Okay? So let's take a toy problem. Let's say you have to make gauge invariant combinations of the letter x. Okay? So how do we do that? Well, if you're allowed one, I'll go closer because of this lag here. There you go. If you're allowed 1 power of the field x, the only thing you can write is trace x. If you're allowed 2 powers, you can write trace x square, but you can also write trace of x squared. These are independent. At 3 powers, you can write these 3 combinations and so on. This list actually grows pretty quick. But the pattern is pretty clear. If you're only allowed the letter x and not y, z, or x bar or anything, the whole list is generated by trace x squared, trace x cubed, and so on. Okay? Generated in the sense of addition and multiplication. All right. So that's an easy problem, and in fact, if you think about it a little better, this infinite list, trace x, x squared, trace x cubed, etc., is not independent. They're not all independent, because if the size of the matrix is n, then trace of x to the n plus 1 by the Cayley-Hamilton theorem is determined by the lower traces. Okay, so only the first n traces are independent, and that's what those are the finite generators. Good. Now, you might think this is a toy problem, but in fact, this is the answer to a physical problem as well, so which is the following. So Fourier-Engels theory has 32 supercharges, and suppose the question is, we have to make a list of all local gauge invariant half BPS operators. Okay? So the answer to this depends on which set of 16 supercharges you have, but for a particular set of 16 supercharges, the only half BPS letter here is X, and therefore this is the complete list of gauge invariant operators. Okay? So that's where this is coming from. And now if you want to summarize all this in some kind of a generating function, so you take a trace over this space of operators, half BPS operators, Q to the Hamiltonian, let's say the free Hamiltonian, then that's just the product over the n generators. So here the nth term, small nth term, just means you have trace of x to the n, which can be multiplied to itself as many times as you want. Okay? And then this, the fact that it terminates at n is because of this trace relation that we just said. All right. So that's the type of problem we want to discuss. I just want to give you a flavor, but already if there are any questions, please do ask. Okay. So now we want to do a slightly harder problem. Instead of one letter, I want to consider the full theory. And in fact, I'll change the problem a little bit. So take the same gauge theory and put it on a compact manifold, S3. And now the problem is to write the partition function, okay, trace of Q to the Hamiltonian. So here H means the Hilbert space of states, but because you have a conformal theory, you have a state operator correspondence, and so this you might as well enumerate it as a list of operators. That's the problem we just discussed in the previous slide. But now you're allowed not just X, but any type of field. And in general, this is a hard problem at non-zero G angles. So because there the problem means you have to diagonalize the Hamiltonian of Youngman's theory. So at n equal to infinity in the last 15 years, integrability, people have made a lot of progress, and the problem is kind of solved. But for general n, this is a hard problem. But in the free limit, this is actually solvable. It's similar to techniques of the type we just saw in the last slide. There's slightly more sophisticated techniques which are available. So let me tell you how to write the answer. Okay, so the answer is that you take this space of single letters that we just saw, and you calculate the same trace on this much smaller Hilbert space of the space of letters. Okay, so this is typically some much simpler function than this one. So if you just have a finite number of letters, it's just some polynomial in Q. If you have derivatives which you can apply infinitely, it's a rational function. Okay, but nevertheless, a simple function. And then the answer is given by this integral. Okay, the partition function, which I'll call I, is an integral over the space of n by n unitary matrices of this exponential, and it's completely governed by this one function f. Okay. So how do we understand this formula? So there are various ways to do it. So from the Hilbert space point of view, you can think of this exponential. So this thing is called the platistic exponential when you have 1 over k. What that is doing is taking letters and forming all possible words from the single letters, okay, including gauge indices. And then finally, the integral over the gauge group projects onto the gauge invariants. Okay, that's one way to understand this formula. Or you can think of this as a Lagrangian formula, where you start with the path integral over all the matrix valued fields, and because G angles is 0, that localizes to only some constant set of matrices. Okay, there are many ways to understand this. I don't want to go through the derivation. And now that's the partition function, and then you can expand it in some Q series here, and the coefficients L here is the Hamiltonian, and the coefficients are the number of gauge invariant operators with that value of Hamiltonian. Okay. Now, one word about the notation is that, so although we know that this problem is some physical trace, and I'm telling you what to calculate, at a mathematical level, the only input that goes in is this function f, which, as I said, is quite simple. I'll show you examples. And therefore, I label this output by if. Okay, so and soon we'll sort of remove sort of the details of where it came from. Okay, and relatedly, instead of Q to the Hamiltonian, I could have taken any other conserved charge, and the same formula is true. Whatever trace you want to calculate, you calculate the same trace on the space of single letters, put it in this formula, calculate this integral, and that's the full trace on the Hilbert space. Other questions? Yeah?
So, perhaps see one. So, in this case, you don't use the PPS, it's just the partition function.
It's just the partition function, but it's free. It's free. So, yeah.
Okay.
That's why you can solve it. All right. Now, that brings me to the next point, which is that, so you can put any conserved charge. If you have a theory of fermions, you can put -1 to the f. You can have more potentials, more charges. Okay? I'll stick to only one potential, but I'll include now -1 to the f. Okay? It's exactly the same formula. So now we want to turn to supersymmetric indices. So a general supersymmetric index has this form. You have a trace over the full Hilbert space, -1 to the f times q to some operator. That operator is some conserved charge made out of all the conserved charges of the theory. So this is n equal to 4 super Yang-Mills, that's the Hamiltonian. These are the SU4R charges. On a sphere, there are 2 angular momenta and so on. Okay? And this is built in such a way that this only receives contributions from BPS states of a certain type. So for example, if I take this operator to be this J2, it turns out that this is a half BPS trace in the sense that this only receives contributions from half BPS operators. Everything else cancels out. Okay, in this case, you can check that the single letter trace, you just go back to the list of single letters that I said and say which ones are half BPS. The answer is only X, as we all know, and therefore, and which has J2 equal to 1. So this single letter trace is just Q, f of Q equal to Q. And you can input this into this master formula. Okay, here instead of f of Q to the K, just put Q to the K. And I leave this as an exercise to show that this is exactly the same generating function that we first wrote down. Okay. Very good. So now throughout this talk, I'll have a running list of examples of this half BPS index, a 1/8 BPS index, and a 1/16 BPS index. Okay, so I'm reducing supersymmetry. There are many other indices possible in n equal to 4 super Yang-Mills. I'm just going to choose these 3. They have been studied a lot. And you can see that the single letter trace increases in complexity. So it's Q, some rational function, some more complicated rational function. All right. Now, why are these supersymmetric indices interesting? Well, firstly, they can be easily, so they're defined at any value of the coupling, but because indices are protected, they're equal to their value at free coupling, and that's why you can use this technology. You can use this formula. But the real interest is the fact that they're also equal to their value at g equal to infinity, j Yang-Mills equal to infinity. Okay? At g Yang-Mills equal to infinity, you have a completely different way of understanding these indices because of the ADS-CFT correspondence. Okay, so this is the same setup that we had. And now there is an ADS dual, which is some type 2B string theory on a space which is asymptotically ADS 5 times S5, whose conformal boundary is the same as 3 times time. Okay? And this has a parameter which is G string, that's G string in ADS space, whose square is G Newton in this 5-dimensional theory, which is equal to 1 over n square in the gauge theory units. Okay? There's another parameter which is the 't Hooft coupling, but I'll be considering BPS quantities, so everything will be independent of the 't Hooft coupling. All right. Now, the idea now is to ask what does this ADS dual picture tell us about the states in the Yang-Mills theory. Okay? And the most dramatic prediction comes from the fact that there are black holes in this theory which preserve 2 out of the 32 supercharges of the theory. Okay? Both the authors are in the audience here. This was discovered about 15 years ago. And these black holes have a large horizon area in Planck units, which means that their Bekenstein-Hawking entropy scales as 1 over G Newton, which is n square, times some function of the gravitational charge L over n square. L is the sort of integer charge, and L over in units of G Newton is the gravitational charge. This is some asymptotic formula I've said when L becomes very large. All right? Now, the ADS-CFT correspondence says that this black hole entropy must be equal to the logarithm of the index degeneracy of the 1/16th states that I just showed you. Okay? And this kind of, whether this is true or not, was posed, this question was posed in these very nice papers about 20 years ago, 15 years ago. And in the last few years, there's been like a spurt of development, and now we know that the answer is indeed yes. And I should say that in verifying this prediction of ADS-CFT, a lot of work went into really trying to understand what exactly does this symbol mean, in what limit is this supposed to be true, why is the index equal to the entropy? So all these questions have been settled by now, and I'm happy to talk about this after the talk. It's not the subject of my talk. Okay? At the end of the day, you have a very concrete prediction, and so that's, lots of work went in. And here's what the answer looks like. So this is a plot of the logarithm of the absolute value of the degeneracies, okay, as a function of the charge. Okay? And this is the U2, U3, U4, and so on. You can keep drawing the graphs. And here is the same index on the space of gravitons, okay, just for reference. And pictorially, the ADS-CFT correspondence says that this sort of scatter plot, these are really numbers coming from Yang-Mills theory. Okay? These are logs of integers, should latch on to the smooth curves predicted by gravity, at least in a certain limit when L is large and N is large. Okay? And you can, and as I said, there's been a spectacular verification of this. In fact, there are surprises. These curves latch on to the gravitational formula even for small l, small n, and these things are being people are trying to understand why that's true. But certainly you can sort of almost eyeball the shape of this. But once you understand all the predictions from gravity in an analytic fashion, you can go and do a gauge theory calculation and even analytically understand that the growth of states of these curves, of these plots, is exactly reproduced by, is exactly equal to this black hole entropy formula. Okay? So that's the nature of the progress that has been made in the last few years. This is not the subject of the talk. It's just that when we're discussing indices, this question always comes up, about where are the black holes? And the black holes mathematically have to do with some kind of asymptotic growth of states of these integers. Okay? Today I want to discuss something slightly more detailed. And the first thing I want to say is that the gravity actually gives you more predictions than just the fact that there's a black hole and there's one asymptotic formula. Okay? But before I go there, any questions about all this? The brown dots are the same, is the same. So this is the index in the U2 gauge theory, U3 gauge theory, etc. This is the same index on the space of multi-gravitons in ADS space. Okay. And I write that for a reason that you'll see later. You can see that this has very little entropy. That's this gas of gravitons. Okay. In the old days, that created some confusion. So I just wanted to, for the experts, I want to show that this actually has very, very little entropy. Okay. And that's also going to play a role. Any other questions? These ones? Yes. I got them by calculating. So I told you what the formula is. This is the F. I have this integral formula which I showed you. I plug in the F, and I calculate these numbers. Like, those are numeric. So those are scatter plots. Those are, every d is some integer. I'll show you the numbers, but these are logs of integers, which I actually calculate to the first 100 values. Okay, it's not very easy to do, but you can do it. So these are numeric. So this I wanted to give you a sense that indeed these curves look like that. But analytically, one can just take the formula, this integral formula that I showed you, and calculate the asymptotic growth of states of those coefficients without actually calculating numerics. And they're perfectly, including all these factors, are governed by this entropy formula. Please.
What's the significance of the very different zoom ratios of two plots?
That's exactly what I'm coming to next. So just hold on that question, please. There was another question? Or not? If in one slide I haven't answered this, please ask again. All right. So what is gravity telling you? So here I've removed the numbers here just because of this question of scale. But now let me tell you in words what is happening. So there are three regimes in which gravity has fairly precise predictions. So the first regime is when the charge, these are BPS black holes, so that you can think of the charge essentially as the mass, more or less. So the charge is of size n square or more than n square. Remember, n square was 1 over g Newton. That's where the black hole solutions are valid. Okay. Then there is, so that's where this entropy formula is valid, and that's what we just verified. Then there's the regime of very small charges. Okay, so in gravity, this means that you have just empty ADS space and then few fluctuations. And the only fluctuations that are allowed in gravity at very small energies are the gravitons. Okay, so that you can calculate. You can take your favorite ADS5 model, ask what is the what is the spectrum of the gravitons? Some group theory calculation, and the answer is, you can calculate it. Okay, this is something, I don't want to stress this too much. It's also in terms of this single letter trace. Okay, you can write this formula. All right. Now, there are two scales here. One is n and one is n square. So, in gravity, this is 1 over g Newton, 1 over n square is g Newton. This scale, 1 over n is 1 over g string, and that's the scale at which you have the first d brane excitation. Okay, that's why I put this cutoff here. Okay, so until you hit the first d brane, essentially the physics is governed by gravitons. Then you have d branes, and then you have black holes. Okay, now so the third regime is what I want to focus on today. Okay, these are giant gravitons, roughly here, but as I'll show you at the end of the talk, in fact, this can be scaled off to infinity. So I hope I answered that question. Yeah. Other questions? All right. So I want to focus on this, and in order to do that, I'll actually show you these numbers. Okay, so take these 1/16 BPS indices. This is the U1 theory. I've just plotted. I've just sort of written down what this index is for the first so many values of charges. Okay, so that's the U1 theory. So D1. Remember, my notation is Dn. N equal 1 means U1. Okay, that's U2, and the black holes sort of live when n is large and L is large, somewhere over there. Okay, that's U3, U4, etc. Okay, so that's your table. And you see one thing that's very striking, that instead of reading the numbers horizontally like you should, if you read the table vertically, you see that at any given value of charge, let's say this one, after some time, the numbers stabilize. Okay, they just become constant. All right? And where that's happening is exactly at a diagonal of slope 2. Right? And the numbers to which they stabilize, you can check, is exactly equal to this index of the gas of gravitons. Okay? That's not very surprising. We'll discuss why in a second. But first, let me show you some more data. So that's the 1/16th BPS index. The same thing happens for the 1/8 BPS index. The numbers stabilize. All right? The 1/2 BPS index, the numbers stabilize. Okay? And in fact, this feature has nothing to do with supersymmetry. It's just a fact about all unitary matrix models of this type. Okay? So first, let's just try to sort of think through why this is happening. This is also familiar to many of you. What is the statement? The statement is you fix charge, and then you go to very large rank. Okay? And this is roughly the number of operators that you can make, gauge invariant operators that you make. So fixed charge means that you have, think of our toy example x. So you can take x, x squared, etc. But if the charge is fixed, you can't do, if the charge is 7, you can't go more than x to the 7. So you have some finite number of operators. But the size you're scaling to infinity, that means that there are no trace relations. Therefore, it's the free module that you can just calculate, and that's what the gas of gravitons is. Okay, that's roughly the idea, and this can be made, but that argument doesn't quite capture exactly where the stabilization happens, and exactly at the diagonal, and you can prove these things. So I'm just going to give you a sketch of the proof. I think this was known to people before, so I sort of wrote down a careful proof in this paper. I think it was known both in physics and mathematics earlier. It's not, I don't claim that it's particularly new. All right, so the way it works is like this. You take this integral formula. Now you expand the exponential. Okay? So in some formal infinite set of terms, and each term will have some powers of trace of u to the case and trace of u daggers to the case. All right? Then what you do is you write those traces of u to the case, these are called power sums, as an expansion in the characters of un. Okay, you can always do that because the characters are a basis of these kind of functions. And the coefficients of such an expansion is given by what is called the Frobenius formula. It's a 19th century thing. The coefficients are themselves characters of the symmetric group on n lattice. Okay, it's a classical fact in group theory, which I call mu here. So my notation is like this: lambda and mu are partitions of integers. The reason that's coming is because you have sort of lots of traces, and the correct label is like you have k1, k2, k3, etc. Some partitions of integers. And these things are characters of the symmetric groups. Remember, the characters of symmetric groups are labeled by partitions of integers. Okay? This is some combinatoric factor. F lambda means that if lambda is 1 to the r1, 2 to the r2, etc., f lambda of q is f of q to the r1, f of q squared to the r2, etc. Okay? So anyway, it's something all of you can work out in 5 minutes. The main point is, so you're still left with the un characters, but now you can integrate that out, because of the orthogonality relation of the characters of un. Okay, so what you're left with is only a sum. So there's no integral. We like this. You've discretized the problem, but without sacrificing any symmetry of the theory. Okay, so it's an exact formula. All right. Now notice that there are two sums over characters, two sums over partitions. One of them is unconstrained. You have to sum over all partitions. The other one has a constraint that the length of the partition should be at most n. That comes from the fact that this thing began its life as a un integral. So the Young tableau has at most n rows. That's what this is saying. Okay. All right. Now, when n goes to infinity, this constraint you can remove, and then you have some second orthogonality relation of the symmetric group. So you can, that becomes 1. This collapses to 1 sum over partitions, which is this infinite product, and you can check that this is the same as the graviton gas. Okay, there's some proof. Again, I don't want to stress the details. The main thing I want to show is that firstly, there's a sum over partitions. So philosophically, it's nice because it discretizes it. But even practically, actually, this is the formula which is the fastest way to calculate these numbers that I showed. Okay, instead of calculating integrals over the gauge group. All right. Any questions about this? All right. So what we've shown, yes.
Question. The table you showed before, does it somehow? I mean, it reminds a bit of like these spot periodicity type things, or I mean, does it somehow relate to things like higher homogeny groups of UN also show some sort of convergence when it.
I'm not sure. You should certainly tell me about it more after the talk. The only comment I have is that there is no periodicity here in this direction or in this direction. Okay, but I would love to hear more about that. So these numbers actually grow kind of exponentially. Any other questions?
Are you going to explain the position?
No, so that I leave as an exercise. So I've given you enough details here. Basically, if you look at what this f lambda is, right, you'll see. So let me instead show you something nice. You'll see that here the diagonal is exactly of slope 1, okay, but for the 116 BPS it had slope 2, okay, and that's related to the fact that this begins with q square and that begins with q. Okay, so I think that's enough hint for a homework problem. Yeah. All right, so I've given all the formulas. So that's in this paper. You can look this. All right. Now it's the same exercise. You have to then say, you have to say how does f lambda scale, and then you'll find that it exactly happens at the diagonal. Okay. Other questions? All right. So what have we shown so far? What we understood so far is that in any of these tables, okay, the input could be any function f. It's a mathematical statement, not necessarily index, not necessarily anything. That the first n coefficients, or 2n, let's call it n, the n coefficients are given by an explicit formula that I wrote down. Okay, I'll call that the graviton formula. Okay, so this physics-wise, what I've explained is the very small states in ADS. I've shown why exactly the boundary theory should capture the gravitons, but all the way until n, at least in the free limit or for supersymmetric things. So the natural question is, what happens next? Is there a formula for the next n coefficients? All right. So how do we do this? Let's look at some data again. So you take this in, I infinity was the thing it's stabilized to, so you divide by it. When you divide by it, you get the first n coefficients are the same, so the first non-zero thing is q to the n plus 1. So you get 1, 0, 0, 0, 0 up to q to the n plus 1, and then you get a second series. Okay, so this I call the subscript 1. And now let's look at this series. So this is a half BPS counting, and you see that just this is some pattern matching, that there is a stabilization. In fact, it's much better than stabilization. They're all constants. They're all -1. Okay. So you might think, okay, this is a good way to proceed. Then let's look at the next one, which is 1/8 BPS. Here you say, well, you see that essentially the same thing is happening. It's all zeros below some diagonal, except not quite. There is this annoying column here, which doesn't stabilize. Okay. All right. It doesn't stabilize, but basically you can eyeball what this formula is. It's with a minus sign, 3, 4, 5, 6, and so on. So it's just n plus 2. Okay. Okay, let's go to the 1/16th case. So now it's the same exercise. You're supposed to come up with a formula for these numbers. Okay. But I did try this in a conference last week where there were number theorists, and people actually started calculating, and, and they did give me a formula. So you can interpolate, you can always interpolate. If you're very fast, like, then you can see that this is some quadratic growth in n and so on. But the question is there an a priori formula with the data of the gauge theory? If I just tell you this is the gauge theory, this is a single letter index, can I say what these coefficients are? Okay. So that's the question I want to answer. And there are these very nice papers of Imamura and collaborators and Gayoto Lee, who gave the name giant graviton expansion. And this is, in these papers, you can see that, so this paper of Gayoto and Lee actually was doing numerical experiments of this sort, trying to reorganize these ideas about determinants. Here, there's a sort of a ADS CFT approach. You say, well, look, this should be the first D-brane. So let's just go to the ADS space, build the first giant graviton, look at BPS fluctuations, and try to calculate. And that works, actually. That gives you these kind of numbers. Okay, it's not completely, I haven't understood everything about it, but that seems to work. But you can ask, well, what about the next n coefficients and so on? Okay, so that's the problem I want to solve today. Any questions? So the red is sort of some pattern matching that I did. That roughly, I think that from the first experience, that something should happen across a diagonal, and I see that in the half BPS case it does, and 1/8 BPS case it does. So I just sort of put some diagonal here without thinking too much about it. It'll be just, it's more observational. Okay, so you'll see at the end why there are these red numbers. Other questions? All right. So that's so the formula is called the giant graviton expansion, and it looks like this. So the context is the type of unitary matrix model that I studied. Okay, it doesn't have to be an index, and in fact, it's even more general. Instead of f of q to the k, instead of one function, I'm just going to give myself an infinite number of letters: g1, g2, g3, etc. So that I'll call the partition function, and if I want my indices, I just put gk equals f of q to the k, where f comes from the calculation. Now, the giant graviton expansion is a second formula for the same partition function of the following type. Zn over z infinity, that's what we are calculating, is a sum over an integer m of some series for which I'll give you a formula. So each of these is an infinite series, characterized by the fact that the mth term in the series has order just in the sense of how many powers of g's there are, m times n. Okay, let me explain what that means. It means the 0th term starts with 1, the first term starts with g to the n at least, the second term in this starts with g to the 2n. Okay? But that sort of naturally suggests that there's some determinant behind the game, right? That if I have n, it feels like it's one determinant. If I have 2n, it feels like there are two determinants. Okay? And that's roughly what this whole game is about. That, remember, in the holographic picture, usually you have something like this, you expand it out, and in holography, you think of them as stacks of gravitons. Gravitons are closed strings are traces. Okay? But you can say, well, you also have d-branes. D-branes are, as Witten taught us, baryons or determinants. Okay? So you can say, what if I take a determinantal basis instead? All right, so that's what is going on. And now I give you, so that's going to be the nature of the formula. And in deriving this formula, I have a third formula for the same object, which lives in a certain free fermion theory. Okay, it's really it's a 1 + 1 dimensional free fermion theory, a chiral 1 + 1 dimensional free fermion theory in the NS sector, whose states are labeled by an infinite set of variables, T1, T2, T3, plus and minus. And in that theory, I'll tell you about an operator which is labeled by n, and then you take the quantum expectation value, and then you take a further expectation value, meaning further average, over the ensemble. So what that means is that, so you take the expectation value in some state t, and then for each t you do a Gaussian integral for each tk, whose weight is gk. Okay? So that's the nature of the formula. Yeah?
Is there a string theory interpretation of why we get this free fermion formula?
So I'll tell you what the derivation is, you will see. So not yet, but that's my hope. So my hope is that, so this we understand where it's coming from. This has some interpretation as d-branes. I can try to give you some words, but I haven't worked them out. They should be some, I mean, we've seen free fermions in gauge theory many times, and one example is the LLM picture for half PPS states. That's one idea of what's going on. So there's some, you're quantizing the system in some free variables. Okay, so let me tell you the derivation, unless there are questions about this. All right. So first, instead of the matrix model that I want to study, I'm going to study an auxiliary matrix model labeled by these infinite parameters T. So why am I doing that? So remember, this matrix model has some trace u to the k, trace u dagger to the k. If you study matrix models, you'll realize that that's a difficult problem, because in terms of the eigenvalues, it means that there's a two-particle interaction and no single particle interaction, right? There's only products of these things, right? Usually, the way we are taught in school to solve matrix models, you have some single particle potential, all the eigenvalues condensed there, and then the two-particle potential sort of makes for a small repulsion. Okay. Here, there is no single particle potential. Okay. So that's what makes this problem hard. This problem is sort of similar, except that now I've linearized the interactions. It's trace of u to the k, trace of u dagger to the k, with some coupling. So this is a much more familiar model. So for instance, if you take the vector of t's to be t1 equal to 0 and everybody else, sorry, t1 equal to 1 and everybody else to be 0, that's the Gross-Witten-Wadia matrix model. Okay? So it's more familiar. But there's a relation between these two models, which should be sort of, you can almost eyeball it, which is that this one comes as a completion of squares of this one. So this is the Stratonovich-Hubbard transformation, right? So if you take a Gaussian integral over tk with Gaussian weight g, then you glue together the trace u dagger. Okay? So the idea is to solve this model and then do the Gaussian integral. All right? Okay. So the same thing can be said in the language of partitions. Remember, I had two sums over partitions, lambda and mu. One of them was constrained, one of them was unconstrained. And the original model, I can think, so forget about this for the moment, just focus on lambda. The original model I can think of as a sum of squares of characters. Okay. The linearized model is a square of sums of characters. Okay. So you can show that this is the translation into the partition language of what I just said as integrals. Now, why we like this is because linear sums of characters are familiar in mathematics. These are called Schur polynomials. In some variables, I'll call them Schur functions. And that we know how to handle fairly well. So I'm going to use some of ideas related to that and then integrate to get that. Okay. All right. So, okay. So the next few slides, they're a bit technical, but it's some nice technology which I think should be known. So I decided to talk about it. So the idea I learned from a set of papers by Okunkov and collaborators. So the first idea is that any sum over partitions, whenever you're faced with a sum over partitions, you can translate that problem into a free fermion theory. Okay, it goes like this. So imagine you have a partition 5, 3, 1, 1, 1. Okay, you rotate the partition by 45 degrees, like so. And then you draw the axes. And this horizontal axis is the Fermi C. And then at every half integer point, you put either a fermion or a hole. So the vacuum state is when you have, so for, electrons are holes, electrons are black. So vacuum state is, it's all black here and all white there. And whenever you have a partition, if you have a line going 135 degrees, you put an electron. If you have a line going 45 degrees, you put a hole. Okay? So this way, one to one, you can map a state in fermion theory, free fermion theory, with these partitions. Okay? And now there's a property of partitions called the Frobenius coordinates, which it's fairly easy to see that in any such thing, the number of excited electrons is the same as the number of holes. Okay? So you can think of every partition as essentially taking some number of electrons from below the C and throwing them up. All right? Good. So here you can see, for instance, this is minus 3/2, that's minus 9/2, that's minus 1/2 and minus 9/2. Okay? These are the excitations. All right. So then we want to study these kind of linear functions of these partitions. Okay, so you take that state in the free fermion theory and label it by T. Okay, and then you sandwich these two such things with some operator called NR. Okay? And any such expectation value will have a double sum over partitions with two Schur functions. But given that these states are orthonormal, that double sum collapses to a single sum. Okay? So you have a single sum of squares of these Schur functions. And if this nr is the excitation number at point r is any half integer, then you can show, that takes a bit of work, but that's what they showed. Then it means that that's in this sum, the only partitions that are left are the ones which contain that half integer r. Okay, so you have a sum over all partitions which contain that half integer r. Okay. Good. So now what we want to calculate is a sum over partitions, squares of Schur functions like this. Yes.
Means that basically there's an election.
Yeah, exactly. So this partition doesn't contain that one, for instance. Exactly. Yeah, 9/2 is in it. Yeah. Okay. So you can have something like that, and then this can go on, and that still contains 9/2. Exactly. Okay. Now what we want to calculate is a sum of these squares of Schur functions with a constraint that L of mu, the length, is at most n. So what does that mean in the free fermion picture? So let's say n is 3. So that's half, 1.5, and 2.5. It means that below 3, you're not supposed to excite anything. And between 0 and 3, you can take any number of electrons and throw them wherever you want. And you have to sum over all these processes. All right? Good. So that means that below 3, so at the sort of, you can only go to a certain depth in the sea. The bottom of the sea, you're not allowed to excite holes. All right? Now, that means that for every r which is so below n, you want the excitation number to be 0. So you put a factor of 1 minus nr, so that if it's 1, it collapses. Okay? So this is some infinite product, and then you can expand that into an infinite sum, and every sum has some 2m point function of fermions. It's m excitation number, so 2m point function of fermions in this state T. But now we're more or less done, because it's essentially a free theory. So these 2m point functions are just determinants of 2-point functions. Okay, that's the Wick's theorem, which holds even, so because it's a free theory, Wick's theorem holds even for an arbitrary state. Okay, so it's just, you just have to calculate the 2-point functions. And the 2-point function needs some calculation. That's what Borodin and Okunkov did. So those are the 2-point functions, and that you can do using bosonization. It's again a free theory, everything you can calculate. So this I won't stress too much. There's some formula. If you've seen bosonization, is the type of formulas that you see in bosonization. Okay. So basically, there's some generating function. It's calculable. Okay. So that's that. And now we want to sort of transform back to the original model. So you have this determinantal expansion, transform back, and that's the final formula. Okay. So there's some determinant here with some prefactors, and you want to do the Gaussian integral. Okay. It's slightly formal, but now you can work this out. And one thing which is already clear here is the fact, so firstly it's an ensemble average, but also the fact that you have to dip in at least m, so the energy excitation of the fermions, of each fermion is at least n, means that the total number of, total energy contained in this mth term is at least m times n, because there are m fermions. All right, so for the first one I actually worked this out in my, so the first non-trivial one, I worked this out in this paper. You can actually massage this Gaussian integral and write a generating function with respect to the rank, and that has this very nice infinite product formula of the type of the usual indices that we usually see. Okay? So the input here are these numbers a hat k, which I call the dual single letter coefficients or degeneracies, whose trace, whose generating function I collect in a function called f hat, which comes out of the calculation. Okay, so the calculation tells me what these things are, and it's a very simple answer, is that f hat is just f over 1 minus f. Okay, so that's the formula, and now you can check it. So let's do the 1/2 PPS index. Yeah.
What does the contributions to the sum for negative n mean?
Nothing. So you're supposed to calculate the n positive. You just do a generating function. Yeah. All right. Well, nothing as far as I know. Maybe there's some interesting thing. All right. So now these are the red numbers in the table that I showed you. This is the my giant graviton formula, and you can see that the first 5 until q to the 5, it agrees. This is n equal to 2, n equal to 3. Of course, these here in this case, the half PPS case, you have an exact analytic formula which is known. It's not so much fun. But here's the 1/16th case for which we didn't know an analytic formula. And again, you see, so that's the numerics that I showed you in the table, and this is the formula that I just calculated. Okay, so you can see there's a precise match for all, as far as I can compute. I mean, I gave a proof, but it's nice to see numbers working out. All right, so that's the end of the story. So let me just give you some comments. So firstly, this new index formula smells like, it feels like a lot like the original index formula, some infinite product of the type, but with some new f. So of course, the natural interpretation is that that's the index of the curved d-branes inside ADS space. All this needs to be worked out. So these calculations of Imamura and friends go in that direction. It also feels a lot like, so you can ask, why did I take a generating function with respect to the rank? That I don't understand the physics of it. I did it because it was nice mathematically, but I don't know what the physics of taking summing over ranks means. But it feels a lot like this level rank duality of Chern-Simons theory. So if anyone has any ideas about that, I would like to understand that. Formally, you can, so one thing that confused me is this giant graviton expansion, is it an open string theory or a closed string theory? What am I counting? Yeah. Because I already have an open string theory, that's the original index. But then so people told me about this work of Gopakumar, who says that for every closed string theory, there are actually two open string theories, there should be. And his prototype was of low-dimensional string theory, two-dimensional string theory, for which there's the double-scale matrix model and the Kontsevich matrix model. Okay, both of them are open string theories, and he has an idea that one of them comes from filling in faces of your sort of Ethoff diagrams, and the other ones at the edges. So that's what this feels like, that the original index is like the double-scaled matrix model, and this formula that I'm giving is like the Kontsevich matrix model at finite rank. We still haven't answered a question of even more detail, which are the operators which form the giants. That will be very nice. It's a hard problem, and I don't think there's a direct attack which will yield results, but maybe these kind of ideas, you can do perturbations. All right. The last point is that these formulas that I showed you, the giant graviton expansion, is not asymptotic. It's a perfectly convergent expansion. Okay, so I can prove that. What that means is that you can go formally. You don't have to stop at level n or 2n. You can go until infinity, which also includes n square. Okay, so that means that those formulas should contain the black hole growth of states already. Okay, so that will be something nice to really understand how that's happening. But that, physics-wise, that's not very surprising. What we are saying, I mean, the whole ADS CFT story started by the fact that black holes are made up of d-branes. Okay. And now we have this ADS5, and what I'm saying is that ADS5 black holes are made up of ADS5 d-branes. All right, so it's a more complicated story, but it's the same spirit. And that's it. Thank you very much. No, so now, of course I knew the answer, so I so you could have asked, yeah, so you wanted some diagonal, and for the 1/2 and 1/8 BPS cases, it was staring in the face that there's a diagonal. 1/16 I don't know, but now I've calculated the answer, so I sort of went back and put.
But technically, what happens when you cross the diagonal?
What happens is that you get, so morally it's like q to the 3n, so two giants kick in. So it's like, remember the formula is like this, 1 plus q to the n, so it's actually 2 for this 1/16th, but let's ignore that for the moment, times, some a0 plus a1q plus ... And then, so remember this is z over z infinity. So those are the gravitons, okay? So really there's a graviton on top of everything. So gravitons, this is the first giant plus gravitons, and then there is this one, the second one. Okay, and it's this one that starts kicking in when that stops. Other questions? Yeah.
Japanese colleagues do what they are calculating.
calculating with the, so they take, I guess, a probe in ADS.
Yeah.
What they do on it, they calculate fluctuation.
Yeah, they calculate BPS fluctuations essentially.
What they can you identify the spectrum of fluctuations with the number?
I'm trying to do that. So, so as I said, the numbers actually work out, but I'm trying to get sort of a more linear map from one to the other.
One more question.
Chris?
Can you look at some other superspectral gauge theories with holographic duals, like conifold theory?
Yeah, definitely. So I was careful to stress that the formalism is actually that I developed is completely mathematical. You can do it for other gauge theories. You can do it for any matrix model. It doesn't have to be gauge theories.
In case of the conifold theory
Yeah.
that is not free, could you still apply the same ideology? So it's a theory that's strongly coupled.
Yeah.
It's in itself
Yeah.
conformal.
Right.
So could you apply the formalism?
The index will be governed by a free theory, the supersymmetric index.
Okay, you will count operators.
Yeah, so that looks like a free theory. Right? Questions?
Can you do it for, let's say, any theory?
Yeah, actually, Gayotto and Lee also worked out some, experimentally worked out some examples for that. You can do that, yeah. Any matrix model, it's a very general class of.
So it says the reduced theory has to be a matrix model.
That's right, that's right. That's my, at least in my formula, I started with a one matrix model, okay, but with arbitrary couplings, any coupling that you want. You can try to generalize it to two unity matrix models, things like this. Yeah.
Why is the operators which form the giants mysterious? Could it just be like some anti-symmetric product of the letters? And then
Yeah, so one giant, it's kind of, it's okay, so if, it's morally it's something like that, some kind of determinant, but now you can have if you have one field, it's easy, right? That's the half BPS case, then it's just only antisymmetric combinations at that weight. But if you have many fields, that question is not, I mean, you worked on this before. Maybe for one giant you can write it, but now you can ask what happens in a non-abelian case, it's not so obvious. Right? To identify those determinantal operators for even in a free theory, but when you have multiple fields, is a highly non-trivial problem. So this free fermion technology of Okunko and friends solves that problem. It tells you that there are determinants of that free fermion, but it's a nonlinear problem. Go.
The distinction between S5 giants and ADS giants?
Okay, that's a very good question. So let me remind you of the old story. So for half BPS giants, there are giants and dual giants. So these are giants which wrap some equatorial S3 on the S5 and something on the ADS5. Now, so there's some duality. Okay, and in all ways of writing the half BPS index, you'll see some signs of this duality. As you go sort of to more complicated examples, that duality becomes harder to see. And for 1/16th BPS operators, there is no such thing. So if you ask what is the class of 1/16th BPS operators, so this was solved by, I think, Sok Kim and Kim Yong Lee. It's not that they live on the sphere on ADS. It's some configuration which goes both into ADS and the sphere.
Thanks very much.
Thank you.
So lunch is at the same place downstairs, and then you back to the back door at 2 o'clock.